Hey guys, and welcome back to this class, Deep Learning Prerequisites, Logistic Regression in Python. In this lecture, we're going to talk about how to update the weights of your logistic regression model to improve its error. So far, all we know how to do is initialize them randomly, which of course isn't going to work that well. We've also seen that we can solve for the weights if we assume that the data is Gaussian distributed and has the same covariance for each class. Generally speaking, this isn't the case, so we want something that will always work for all kinds of data. Let's talk about what we did for linear regression. We took the squared error, calculated its derivative with respect to the weights, set it to 0, and solved for the weights. With the cross-entropy error, we can still take the derivative, but we can't solve for the weights when we set it to 0. You are welcome and encouraged to try. So what can we do instead? Well, let's say we have an error curve, and we've randomly initialized the weight to some point. Suppose the derivative at this point is -1, and suppose the point is at -2. Well, the idea is we want to take small steps in the direction of the derivative. The step size is what we call the learning rate. Let's set that to 1 for this example. So the update becomes -2 minus 1 times -1, which gives you -1. So our update becomes -1, which brings us closer to the optimal point. We just keep doing that until we get to the bottom. Notice that the derivative at the bottom is 0, so once we get there, the weight won't be updated anymore. What's cool about this method is that it works for any objective function, not just logistic regression. So we're free to create arbitrarily complex models, and as long as you can calculate the derivative, you can get the solution. Now, if you don't like calculus or you aren't good at math, I feel your pain. But just remember that calculus is really at the heart of deep learning, and a lot of machine learning and statistics. So if you really want to get good, then you want to brush up on your calculus. One question I get sometimes is, how do you choose the learning rate? Unfortunately, there's no scientific way to give you an exact learning rate. You just have to try different numbers and see what works. So how can we do gradient descent for logistic regression specifically? Well, let's start with the objective function. We know that we want to find the derivative of this with respect to each weight. One convenient rule of calculus is the chain rule, so we don't need to do everything all at once. We can first find the derivative of j with respect to y, then we can find the derivative of y with respect to the input of the sigmoid. Sometimes we call that the activation, so we'll call that a. Then we can find the derivative of a with respect to the weights. When we're done, we can just multiply them together to get the final answer. So let's do that. So the derivative of j with respect to y is just t of n over y of n minus 1 minus t of n over 1 minus y of n. This is because the derivative of the log is just 1 over the thing inside. Next, we need to find the derivative of the sigmoid. The first step is to use the division rule, so we get -1 over the thing on the bottom squared. Then we take the derivative of the thing on the bottom. Notice how we can express this all in terms of y, since if we separate the terms, we get 1 over 1 plus exp of minus a, which is equal to y, multiplied by exp minus a, over 1 plus exp minus a, which is equal to 1 minus y. So in total, we get y times 1 minus y. Next, we want to take the derivative of a with respect to w. To make it simple, let's just do this for one component of w, wi. This is just a linear function, so the answer is just x of I. Finally, we can put all this together. Notice how in the first term, y cancels out on the top and bottom, and on the second term, 1 minus y cancels out on the top and bottom. Once we do that, we can multiply through and combine all the terms to end up with y minus t. So in total, the solution is y minus t times x of I. Since each ith component on the left side only depends on the ith component on the right side, we can write this in vector form. So the derivative with respect to w is just the sum over all n, y minus t times x, where x is a vector. This is more efficient because in Python, using a NumPy operation is faster than a Python for loop. Note that you can vectorize this further. Remember that a dot product is a summation over an index. Perhaps we can further vectorize this expression. Remember that X is an n by d matrix, and Y and T are both n by 1 matrices. W is a d by 1 matrix, so we want our result to be d by 1. We can achieve this by writing X transpose times Y minus T. This is a d by n matrix times an n by 1 matrix. Since n is the inner dimension, it goes away and you're left with the outer dimensions, which is d by 1. Now what happens with the bias term? In logistic regression, it's easy to incorporate the bias term into X itself, just by adding a column of 1s. But let's say you want to find its derivative explicitly. Well, we can return to our original expression and just remember that all the x zeros are 1. This just gives us the sum over all y minus t.